Hello everybody, my name is Vicente and today I will be joining you in our lesson about radiation waves. The first term we're going to learn is what is radiation. Radiation is defined as the emission of energy as electromagnetic waves or as moving subatomic particles, especially high energy particles which cause ionization. Some examples of radiation waves are radio waves, microwaves, infrared radiation, and gamma rays. Radiation waves also include nuclear radiation. Nuclear radiation is defined as radiation in the form of elementary particles emitted by an atomic nucleus, as alpha rays or gamma rays, produced by decay of radioactive substances or by nuclear fission.
So, before we learn more about nuclear radiation, we need to understand some basic nuclear radiation terms first. And to do so, I'm going to use these little balls in order to describe how alpha and beta particles work. So, the first concept I'm going to be explaining to you guys is the concept of beta particles. Beta particles are basically high-moving, high-speed electrons, and when they come in contact with any other atom surrounding it, they will spread the radioactivity onto them. It will also make this atom spread around the whole cell, spreading the radioactivity even more. So we can see if we make this ball hit against these two other balls, it will spread around the whole cell, and therefore it will increase its radioactivity. In order to describe the concept of alpha particles, what we're going to be using is a lighter and a candle. And how does this relate to alpha particles? Well, it's pretty easy. Alpha particles are characterized as small particles that don't cause any harm unless they come into big quantities with the surface that they're making contact on. So, here we see a candle. There's nothing wrong with it. And if we add a little bit of fire, it will take some time for it to start to melt, right? We can see that nothing is happening over here. But if we leave it on for some time, or if we add more fire to the candle, in this case, we can see them as alpha particles. We'll see that it will start melting more and more and more. What was once solid will start deteriorating and will start losing its condition due to the high quantity of alpha particles that are making contact with it.
Now that we understand this concept of alpha and beta particles, how do we use this to our advantage, and how do we find out how strong radioactive waves actually are? In order to actually find out how strong these waves are, we first need to find the frequency of the waves. So we will use this formula to modify it and first find the frequency so we can later plug it into Planck's equation. In order to find the frequency of the wave, we will need to divide the velocity by the wavelength. Now that we have our frequency established, all we need to do is plug it into Planck's constant, otherwise known as the equation E equals h times v. H is established as Planck's constant with a value 6.626 times 10 to the negative 34. After that, we just need to multiply it by our frequency and we'll be able to find out the true energy of a wave and how strong it really is. In order to explain another concept of nuclear radiation, I will be explaining the concept of gamma ray bursts. Scientific studies have shown that gamma ray bursts occur whenever a black hole starts to form, and these bursts have more energy in 1 second than the sun will have in its entire life. These bursts are so powerful since they're concentrated with gamma ray energy, and as we know, gamma ray energy is at the end of the electromagnetic spectrum, making it extremely radioactive and really powerful. These bursts are so powerful that calculating their energy would be practically impossible, since they have such a high frequency that the energy they would exert would be a ridiculous amount of energy. We've been lucky enough to be so far away from gamma ray bursts that they can reach us when they happen. It may take more than 4,000 light years for them to reach Earth, but the radiation they exert is so powerful that it could destroy the whole solar system in seconds. The ozone layer would be useless, it would literally have no effect. The thing with these gamma ray bursts is that the gamma energy doesn't disappear. In fact, they grow wider the more they exist, and they don't stop. Eventually, they'll grow so wide that they will be able to destroy solar systems like nothing if they cross their path. But right now, we can't be sure if a gamma ray is headed for us, so we simply just have to live in the moment and enjoy our life. Finally, I wanted to say thanks for watching, and I hope you learned something or two about radiation waves and the effect they have on us.